to our good old friends at PhET, and we're going to use the fluid pressure and flow simulation, but we're going to do the water tower tab and use it to try to figure out Torricelli's theorem. So I've got this tower. I can change the vertical position. And you'll notice that I can have water squirting into the top here. And I've got a way that I can have water squirt out here. I can measure the height with the ruler, the vertical position of this hole, I should say, also the depth of the water. And I can also use the measuring tape to measure how far the water goes. So let's head on over to that simulation and take a gander at what information we can find out. So here we are at that simulation. You notice that we're at the fluid pressure and flow simulation at PhET again, and I've clicked on the water tower option. And what I'm interested in doing is seeing how can I change this range. In this water tower has a fluid depth of about 10 meters. And you notice that the hole is about 10 meters up off the ground with the ruler. And the range of the water is about 19.59 meters. What can I do to change the range? Well, one thing I know I can do to change the range is I can change the vertical position. As I change the vertical position, you notice the range increases. Now, is that a fluids thing or is that just a projectile thing? That sure seems like a projectile thing. That if I throw a ball off of a taller building, it's going to go farther than if I throw a ball off of a shorter building. Well, what else can I do to change? Let's get that range back out to about that 19.59 that we had before. There we go. What else can I do to change the range that would perhaps be more related to the fluid? Well, let's turn off the water and see what happens as the depth of the fluid changes. You'll notice as the depth of the fluid changes, that the range changes. What would be possibly changing the range? Well, let's use this speed measuring device and see what happens to the speed of the water as the depth of the water in that water tower decreases. You notice that the speed decreases as well. Let's head on back over to the presentation and see how we can use Bernoulli's principle, simplify it down, and get Torricelli's theorem. So at the top, I've written Bernoulli's equation, Bernoulli's principle, long equation, pressure 1 plus rho g y1 plus 1/2 rho v1 squared is equal to pressure 2 plus rho g y2 plus 1/2 rho v2 squared. Let's first off indicate what position 1 and 2 is. We're going to say position 1 is at the top of the water tower where the water is going in. And we're going to say position 2 is where the water's squirting out of the hole. Now, first thing that I can say is that at both those positions, the pressure is atmospheric pressure. And so pressure 1 and pressure 2 are equal to one another. So I can cancel those out of my equation. The next thing I can say is that let's just say the vertical position in the water at position 2 is 0. So I can get rid of y2 is equal to 0. I can get rid of rho g y2. And if I'm continually filling the top of the water tower, or if I say that the speed of the water at the top of the water tower is slow, I can say that v1 is approximately equal to 0. And so I can cancel that portion of the equation. And then I'm left with rho g y1 equals 1/2 rho v2 squared. And if I solve that equation, you'll notice that I get v2, that's the speed of the water leaving the water tower, is equal to the square root of 2g delta y. Well, what's delta y? Delta y is the depth of the water. What's fascinating about this equation is this is the same equation that you use to figure out how fast something is traveling when you drop it from a particular height. That if I have gravitational potential energy at a particular height, and it all is converted into kinetic energy, so my mgh is equal to 1/2 mv squared, I get the same equation. It's as if water at the top of the water tower has gravitational potential energy, the water earth system, and it is converted to kinetic energy as it falls, in effect, in the water tower. That's fascinating. So how can I use that to figure out where to place the cup? Well, I already know how fast the water's leaving the hole in my beaker or pop bottle, however you want to do it. And my Torricelli's theorem equation is V2 is equal to the square root of 2g delta y. In this case, the delta y is the depth of the hole, which is h. But how can I use that to figure out my x? Well, my x is my range, and I know that my range is the horizontal speed multiplied by the time it's in the air for. Well, in this case, the horizontal speed is the square root of 2gh. In this case, the h is the depth. Very important that we're focusing on what that h is. But how can I figure out what the t is? Well, the t is just, I can get from kinematics equation, the square root of 2 times the vertical position change as it flies through the air, which in this case is d in this picture, divided by gravitational field strength. So my x, which is my range, is the square root of 2gh multiplied by the time, which is the square root of 2d over g that I get from kinematics equation. It's a neat little lab that you can do with just a 2-liter pop bottle, poke a hole in it with a nail, have water squirting out. Pretty easy lab.